Hi, everyone. Thanks for inviting me. Thanks for coming to the talk. I'm going to present a paper we published recently at ICML called Thinking Like Transformers, in which we basically attempt to create an abstraction for the Transformer-Encoders so that we can start to discuss its power, how it approaches different tasks, and I guess I'll get into what I mean by that in a moment. So first of all, I want to just say, so what's our motivation? There's this thing called a transformer, which is very, very good at sequence processing. It's this highly parallel neural network architecture for sequence processing. It trains well. It's got amazing results. It's fast for training, at least, I think. It's very popular. And with this rise in popularity and success, there comes a question of how is it achieving these things? What is it actually doing? And we're going to focus this question just on the transformer-encoder, which means more on the processing the input rather than the generating the output response. So that's why we say the motivation is on the transformer-encoders. So what do people already know about transformer-encoders? Well, for example, there was one paper that asked, are transformers universal approximators of sequence-to-sequence functions, in which they showed that for any sequence of input vectors, a transformer can map any function from a sequence of fixed length of input vectors to a different sequence of fixed length of input vectors. So they can do anything for a fixed length, which is nice. That's for the encoders. A different paper showed that when we assume hard attention, which we'll explain in a moment, then actually the transformers are quite limited and can't even compute things like parity. A different paper showed that in practice they have difficulty with some regular languages, and on the other hand, do well on other context-free languages, so there's something interesting going on there. And there's also papers which are also interested in the transformer-encoder together as a whole, which actually show Turing completeness in certain sentences, in certain aspects. So we have all kinds of results about the power of transformer-encoders, but these don't really give an intuition of how they're doing all these things. So that's actually what we're going for. So again, the motivation sort of comes from what we already have from RNNs. So RNNs have this known parallel with finite state machine at this point, and throughout the entire lecture, I'm happy to be interrupted, to have questions and so on. Is everyone familiar with finite state machines, RNNs, has a general idea of why these two would be similar? Am I being heard?
You are being heard.
Okay.
There's a question in the chat.
It means recurrent neural network. It means recurrent neural network. It's an RNN. You see the RNN cell there in blue. An RNN is simply a neural network architecture that takes two vectors and outputs another vector, and we assign meaning to these vectors. One of the input vectors is a hidden state. Another of the other input vector is the input token, and the RNN takes these two vectors and creates the next hidden state. So it's sort of this stateful architecture that processes input tokens one at a time, and this can be sort of reminiscent of a finite state machine. A finite state machine, you say you're not familiar. So a finite state machine is effectively just a set of states with transitions defined between them. That's what you're seeing on the right. It has an initial state, and it processes an input token by reading, it processes an input sequence by reading the input tokens one at a time and just following the arrows between the states, giving a classification on the entire sequence based on the classification of the final state reached by following the states in this way. So for example, for the machine on this slide, for the input sequence AAC, we would begin at S1, which is the initial state, read the first token A, which would take us to S2, read the second token A, which would keep us at S2, and then read a third token C, which would take us to S4. S4, the double ringed state, that generally marks the accepting state. So AAC would be a language accepted by this finite state machines. Oh, I'm sorry. You know FSMs. Have I clarified recurrent neural networks? Great. Okay. So because recurrent neural networks have this sort of stateful behavior, it's quite similar to finite state machines. And then we get all kinds of results from this similarity and all kinds of inspiration. So one thing that we get from the similarity is extraction. We try to convert a trained recurrent neural network into a finite state machine that describes the language that the recurrent neural network can recognize. So there's extracting deterministic finite automata like what I've just shown, the example here, but there's also weighted finite automata for RNNs, which don't give just a binary classification, but rather are like language models, give a probability for every next token. So there's a spectral extraction to create a weighted finite automata. There's DFA extraction and all kinds of methods. So there's all kinds of things going on there, and it's nice because we get to convert the RNNs to something that we understand better than a neural network. Another thing that we get from this relation is analysis of expressive power. So there's works showing that second-order RNNs are like weighted finite automata. There's work showing that different RNN architectures are like finite state machines or like finite state machines augmented with counters, and these have different expressive powers, so we get a difference between these two architectures. More works on these architectures also exist. And there's also inspiration from this, because we know that finite state machines are quite limited in their power. They only recognize regular languages. Then we get this idea that maybe we should be augmenting them with stacks, because we know that pushdown automata are more expressive. So there's this idea of creating stack augmented and recurrent neural networks, and that's also inspired from this relation. And all of this is great, and we don't have it for transformers, so it would be nice. The next slide is just a list of papers, just expanding on everything here. So it's a slide for screenshotting only. It's not a slide I'm going to discuss, just a list of papers for those who are interested. I'm just going to put that up for a few seconds. We've got the PDF shared, so we can continue. Okay, so we know that recurrent neural networks are like finite state machines. What's a transformer-encoder like? And maybe at this point you would say, we don't know what a transformer is like, or maybe you do know what transformers are like. I don't know your familiarity with the actual architecture in this group, so we are going to go over the architecture as we discuss this abstraction. So who has an idea what transformer-encoders are like, or what they should be described as? Maybe it's too rhetorical a question. I'll continue. Okay, so what's a transformer-encoder do? Unlike a finite state machine, which reads its tokens one at a time, a transformer-encoder takes its entire input sequence at once and processes all of these tokens in parallel. And it just applies this kind of parallel processing a finite number of times, just using the same type of layer again and again, of course, with different weights, until it has a final output. Okay, and if we'll look a little bit closer at what happens, we get an input sequence like I like dogs. We apply two kinds of embeddings to the sequence. The first is an embedding of the actual word, so that's I like and dogs. And the second is an embedding of the position of these tokens, because we will see soon that the transformer actually doesn't recognize positions in itself, so we have to tell it the positions. And we combine these two embeddings to create an initial encoding of our input sequence. And then we pass it through these encoder layers a finite number of times, actually, the number of layers that we have in our transformer. So this thing doesn't feel like a finite state machine. It's not taking the tokens one at a time. It doesn't have states. What does it have? Who has an idea? So instead of states, it has a sense of information that is being propagated. We begin with this very, very basic information of this word is at this position and that's it. And it's being somehow processed in each layer, creating, I'm sorry, more and more information. So what would we describe this as? This is kind of like, I'm sorry. Is there a question?
Yes. So I'm not familiar with transformers, so thanks for the explanations. I don't have a good sense for the N, right? You know, would we want to have very many layers, and it's just a matter of computational power that we don't, ramp up N until the whole thing stabilizes, or somehow some N's work better than other N's, and we might want 10 but not 20. Does this make sense?
Yes, I am not the right person to ask.
That's okay. So I was hoping, but it's fine even if you don't know the answer.
I expect that if the number of layers is too large, you would have difficulty training it because of vanishing gradients and so on. But you have transformers with 36 layers, maybe more, so I wouldn't know what the optimal number is. Certainly, I expect that power increases with more layers, but also probably the difficulty of training as well.
Right. Thanks.
No problem. Again, not the authority on these things. What do we have? We have this information that's being propagated. It kind of feels like a program, kind of like a given transformer is a sequence of code or a code segment, right? It begins with these very initial inputs, and it processes them, creating more information until eventually it returns, its result. So maybe we should abstract the transformer into a programming language, and that's really what we're going to do. And so in this talk, I'm going to present RASP, Restricted Access Sequence Processing, our programming language that is supposed to replicate a transformer-encoder's behavior, more or less. And these are going to be the main parts. So a transformer-encoder, as we have just seen, is a sort of sequence-to-sequence function. It takes an input sequence of some length and returns an input sequence of an output sequence of the same length. That's different from the transformer decoder, for anyone who's familiar with that. Each of its layers are sort of applying operations to this sequence, and RASP is going to describe the kind of operations which we can apply. Let's begin with the input sequence in RASP. So what do we have in a transformer? The first thing we have is embedding the input tokens and the input positions. And so RASP is going to effectively have every code segment begin with two sequences that describe these two facts. So we're going to have tokens and indices, which are sequence operators, these sequence-to-sequence functions that just describe the input and the position. So tokens on hello is simply the same tokens, hello, H-E-L-L-O, and indices is just their positions. And what you've got here is just a sort of display as you would see in the REPL of RASP. It always gives you examples, otherwise it's very hard to follow what you're making. Okay, so that's the initial input sequences. And now we're going to have to see how we can manipulate them. And to see how we can manipulate them, it's time to look inside the Transformer-Encoder Layer and see what it's doing. So this is a Transformer-Encoder Layer. There's a lot going on. Let's look at the bits one at a time. The first thing I'm going to focus on is the feed-forward sublayer. Basically, it takes every input vector, transforms it using a two-layer MLP, and gives the output. And what we know about multi-layer feed-forward networks is that they are universal approximators, which means that for pretty much any reasonable element-wise function that we would want to do, it can probably be approximated with a feed-forward layer, provided the input domain is bounded, and there are assumptions, of course, but generally speaking, if we're reasonable, we can do anything element-wise. So, so in RASP, we're going to allow ourselves to have any reasonable element-wise operations, or just most of the known atomic operations from, say, Python. So we've got addition, multiplication, power, comparison, all kinds of things. So, for example, we can add 1 to the indices, or we can compare our tokens to E or to 0 and do, logical OR and so on. Are the examples clear? I hope so. For example, on hello, we get true when comparing to E and to 0 on the positions for E and 0, and everything else, E0, O, and everything else is false. So we have our element-wise operations, and we have our initial sequences. That's what we've got. It's not clear from the example, or maybe it is. The OR is a combination of 2 different sequences, right? So we don't just have to do these operations with atoms. Have we got everything that a transformer can do yet? Or in fact, just generally speaking, is this a very powerful language at the moment? The answer is no, because we have stayed element-wise. So in fact, what we have so far, I can't even tell you the length of the input sequence, because at every position, I only know about myself and the token. No matter how many combinations and changes I do there, I still only know the token at this position and the position I'm at, which isn't very much. So let's take a look at the Transformer-Encoder Layer. It can't possibly be all element-wise, else the transformer wouldn't be so popular. And there is one part of the Transformer-Encoder Layer that is not element-wise, and it is the multi-head attention. So we're going to take a look at that. So multi-head attention is a simple combination of a lot of single-head attention. So I'm going to actually start from a single-head attention. So what's a single head? It takes our sequence of input vectors. So this would be the encodings of I, like, and dogs at the appropriate position. And it does the following 2 operations, or several operations, beginning with these 2. We apply an element-wise linear translation to each one, once with a matrix Q and once with a matrix K, creating a sequence of query vectors at the top and a sequence of key vectors. And now we're going to compute scores, relevant scores, between every pair of positions using the query and key vectors. So for the first position, we're going to take its query Q1, and we're going to compute the scalar product of Q1 with each one of the keys. So with K1, with K2, with K3. And this gives us the scores of how interested position 1 is in each of the other positions, including itself. And then we're going to take these scores, which are values in the reals, or however refined a computer can be, and we're going to normalize them to, this is good for training, we're going to normalize them, and then we're going to softmax them. And that's going to give us a distribution rather than a set of scores. And using this distribution, we're going to go and gather information from the other positions for the output at position 1. So we apply a final translation V to each of the vectors, creating a set of value vectors or candidate output vectors. And then we're going to average all of these vectors with the weights that we've computed for position 1 to create the output at position 1. And then we're going to do the same for position 2, so this time with the second query vector, and then again the same with position 3, so that's the third query vector. And that way we have a single attention head that basically takes every position, focuses it on other positions according to its own query, and then averages information from those other positions into its output. What is decay and normalize? Decay is the size of the query and key vectors. So that's D key. The query and key vectors have to be the same size because we get a scalar product between them. So in order to compute the scores. dv is the size of the value vectors. Almost always, dk and dv are the same as dx, not because they have to be, but just because there would be so many parameters, hyperparameters in transformers if we didn't fix so many of them. And so one of the many things that gets fixed is they're all the same, leave us alone. Okay, so that's a single head. So it basically goes out, gathers information, averages it into a position. And now, what's a multi-headed self-attention? It's basically just applying several heads and concatenating them. And how we do that is we take our initial input and we split it into h equal parts. Again, they don't have to be equal, but it's far less hyperparameters if they are, with h being the number of heads. So we split up our input vectors, we send them into the h different heads, and then we just concatenate the outputs back. So they're not interacting in some way, these heads. It's not important that they happen next to each other, and that's one thing I want to say. The multi-headed attention is not an increase of power in itself. It just allows us to compress multiple operations into a single layer. So maybe it makes one layer more expressive, but in the general sense, it's not something that we couldn't have done with many layers if we ignore potential difficulty in training. And so because it's not increasing power, then we're not going to think about this multi-headed attention in RASP. It's not going to introduce operations of its own. It's just going to be interesting in compile when we understand how the code we've created relates to an actual transformer. So let's look at one head. So what do we have? We sort of have two operations. At first, we create a distribution, and then we create values which will be averaged. So the first thing we're going to describe is creating this distribution. And we're going to call it selecting, because we're going to make this simplifying assumption that we don't create scores over the other positions, but we only do a sort of binary decision. Am I averaging from you or am I not? Are you in or are you out? And we're going to describe this scoring behavior with a select operation. How does a select operation work? We take two sequences. Here I've described them explicitly. So the sequences are, for example, 2, 0, 0, and 0, 1, 2. Which effectively describe the query and key values, but not quite. I'll explain in a moment. But intuitively, they describe the asker and the place from which is being gathered, and a relation that we are interested in between them. So here I've got 2, 0, 0, 0, 1, and 2. And the relation is equality. And that's going to create this selection matrix, right? The distribution that we have in the real transformer as follows. So the 2, 0, 0, the first value refers to the keys, that is describing the positions from which we gather. The second sequence describes the queries, that is the positions into which we will gather. And we're going to get this matrix at the first. So we've got the keys, the positions from which we gather, and the queries, the positions into which we gather in the relation. And now at the first position, we've described the position that wants to gather 0, anything that's equal to 0 in the positions being gathered from, and so we select the last two positions. The second output position wants to gather anything that is described with 1, and I've accidentally highlighted the 0 that shouldn't be there, so it selects nothing. And the third output position wants to gather from everything described with 2, and so it only gathers from the first position. So that's a select operation. But it doesn't have to be equality, because these are only sort of intuitively the descriptions. It's not actually the scalar product behavior in RASP. It will be translated differently. So for example, I could have the relation not be equality, but rather greater equals. Depending on how well I'm explaining, who thinks this is reasonable, that I have a relation other than equality? how would I describe greater equals, for instance, if my select is indices, and greater equals, how would I describe that? So I've described a relation that isn't, I can't with the scalar product compute if something is greater or equal to something else. That's not what the scalar product means. But what actually happens if I wanted to describe this relation in a transformer is I wouldn't actually have the indices as the query and the key. I would make sure that my query and key compute vectors such that the scalar product creates this relation. For example, as a simple example, and one that wouldn't perfectly translate you to the softmax, but would hopefully get the point across, I can encode my indices when I'm describing their keys as simply one-hot vectors of the positions, and my queries when I'm as multi-hot vectors. So for example, if I want at position 3 to look at all positions before 3, then I would have a query that's actually 1, 1, 1 to cover all of 0, 1, and 2, and then 0 from then on. So the query and the key won't look exactly like they look in the select. Maybe I'm getting ahead of myself at this point. But it's reasonable to have relations other than equality. So this is how we describe the scoring matrix. And then once we've created the scoring matrix, then we want to aggregate the values that we've selected to average them. So we describe this with an aggregate operation, which is, again, it's going to take the selector that we've created before. That's the first input to it. And the second is going to be the values that are being averaged. So what the selector is going to do is it's going to filter the values. So we copy them for each output position, and then we filter them according to who gets selected. And then we average them to create our output. And there's an aside that if nothing has been selected, so it's been fully filtered, then we put in a default value. And then there's a question of how that's implemented in a transformer, which I hope is reasonable, but we won't get into here. Okay, so that's how an aggregate operation works. And then with these two operations, then we finally have non-element-wise operations in RASP, and we can create sequences that begin to mix and combine information from different positions. For example, I can reverse a sequence, and this also brings us to a point that the aggregate operation is symbolic, which means if I only select one position when I filter, then I'm not going to try to do the average. I'm just going to give you that output, and that allows us, if we have encoded some value as a number, because that's how it will be encoded in the underlying transformer representation, not to worry about going into the number and coming back out. So for example, reverse, I can create flip. So here I've put, for the queries, I've put the indices, that's the dark green. For the keys, I've put the indices in reverse, that's the light green. And I've created a selector that basically matches each position to its opposite position. And then to aggregate, I've simply used the flip selector to filter the tokens in reverse order. And then it hasn't tried to average these values, it's just carried them over neatly, and I've reversed my input sequence. Everyone with me so far? I hope so. Okay. So we just had this example. How does this look in RASP? So flip would be selecting the inverse of indices according to themselves, which gives us this reverse selection. And then we just aggregate the tokens with flip in order to reverse our input sequence. Our select decisions are pairwise. So I've got a description of the query, a description of the key, a description of the relation I want. What would happen if my select decisions were not pairwise? The answer is I would sort of lose the relation to transformers, because if we look at transformers, we're making pairwise decisions about who to look at. And if I was allowing completely arbitrary select decisions, then I would, I could do something completely Turing complete in my attention, so to speak, in my selection, and then just focus it on the correct answer. So I could solve anything if I wasn't restricting it to be pairwise. Okay, does anybody see anything suspicious in this example? Hint, I've computed the reversed indices as length minus indices minus 1. The suspicious thing is that we've never seen length. It's not a part of the input to a transformer, so it's not clear where it's coming from. If someone raised their hand or anything, then I've missed it. Okay, so we're going to have to get to how length got there in a minute. All right, so that's basically all the parts of RASP. So we have the initial sequences, which are basically indices and tokens, and we'll see that RASP actually also provides length in a minute. We have the feed-forward sublayers, which basically translate to basically any element-wise operation between different sequences. And we have the attention heads, which translate to the select and aggregate operations. There are also other parts in the transformer sublayer. So, for example, we have the skip connection, the residual connection. Nothing too fancy isn't the right way to describe it. It is an important part of neural networks. But most importantly, this skip connection, what it does is after some computation has been done, it doesn't, so we've got a sequence of vectors, we do some manipulation to them, and then we have the output sequence of vectors. So the skip connection adds to this output sequence of vectors the original vectors. And this allows us to have the computation be purely focused on creating new information, because the skip connection is going to do the retention for us and add back the information that we had afterwards. So this encourages the idea that we're kind of like a programming language. The variables that we create are still available even after we have computed new variables. Okay, and there's something called LayerNorms, which are, I guess, the bane of my life. They're an element-wise operation. They sort of normalize the entire set of input sequences to a sphere, or something like that. They normalize, yeah. And it's not really clear what exactly this means with respect to expressive power. It does help the transformer train, but I'm not sure whether I should be incorporating this in RASP somehow, what it would mean. So we kind of skip over LayerNorm for now, hoping that it doesn't affect negatively the power in the transformer. But it is an open question whether we should be dealing with it in some more serious way. Okay, and so all of these, what do they become? They've become the initial sequences, that's at the top there. They've become what are normally atomic operators now as element-wise operators combining entire sequences. That's what we've got on the right. And they become the select and aggregate operations, which we have at the bottom left. And now we'll do a small example which shows why length was legitimate in RASP. So if anyone has any idea how to compute length, then now is the time, but I won't wait too long because I do want to continue if not. Okay, so how would we compute length? There is a hint. We're going to use an indicator for whether the index is the first index or not. And here's how we're going to go. We're going to create a selector that focuses every position on every other position. So we've described the queries as one, the keys as one. We want equality between them. We're looking at everything. And now what we're going to do is we're going to average this entire sequence while sending a 1 only from the first position. And what does this give us? So we filter nothing. We average 1 and a bunch of zeros, where the total number of values being averaged is the total length of the sequence. And so we get 1 over the length of the sequence. And so let's write that in RASP. We're going to aggregate the full selector with the indicator for the first position. And we're basically going to get 1 over the length of our sequence. And then with our element-wise operations, we're going to recover the actual length by just doing 1 over that number. Okay, hopefully length was understood. And now we come to the question of, okay, how do we've written some code in RASP. How does this look in a transformer, or at least how should it approximately look in a transformer, because our conversion isn't complete. So indices and tokens are the actual inputs. So we don't need any transformer layers. That's just the first thing that the transformer receives. Select aggregate pairs have to wait until their dependencies are ready, right? So if a selector uses something like the indices, and you can't have the select come before, so indices is already there, but if it uses something like length, we can't have that attention head happen before we've computed length. So our dependencies have to be in the right way, so that's an attention head that would come later. And feed-forward operations don't increase layers because there's a feed-forward sublayer in every transformer layers. In every transformer layer, though I think I may have gotten them the wrong way around. So, you know, first feed-forward. No, it's first attention then feed-forward. I'm sorry. So they don't increase layers. They just have to be attached to wherever their dependencies are finished. Whereas attention heads have to start a new layer in order to get into that multi-headed attention area. Okay, so how would, for example, the reverse that we've computed look? The first thing we do is compute length. So for that, we create this full selection pattern. And then we get our length fraction when we aggregate with just 1 from the first position. And that gives us length. And then we compute the inverted tokens with a feed-forward layer. That's length minus indices minus 1. And then, having computed that, we can go into our next encoder layer and begin the attention head with this reversed attention. So indices matched to the reversed indices. And then when we aggregate from that, we get our reversed input sequence. How does this relate to actual transformers? Are our RASP programs predicting the right number of layers? Are they predicting relevant selector patterns? So the answer is, at least sometimes we are indeed connected to reality, so this language isn't completely out there. For example, in reverse, we found that we first compute length in a single layer, and then only having computed length, we can create this flipped attention in the second layer. So we would expect that reverse requires 2 layers. And now we are going to train a 2-layer transformer on reverse of different input lengths and see what happens. So when we take a 2-layer transformer, we get almost 100% accuracy within 20 epochs. But when we have a single layer, we see that it simply doesn't succeed on the task at all, even if we compensate for the number of heads. So we have 1 layer with 2 heads, and we increase the number of parameters, and we try to be as fair as possible. It just can't do it with 1 layer, which matches how we described reverse. And moreover, if we look at the 2-layer transformer, the one that successfully learned reverse, we get attention patterns that are similar to what we expected. So the first layer has this kind of uniform attention from which it was gathering, you know, 1 from a single position to compute the length. And the second layer has our reversed attention. Now, not every time we trained the transformer on reverse, we got uniform attention. So I think it figures out all kinds of different ways to compute the length, but sometimes it seems similar enough to be nice. There was a, yes, what is it?
Yeah, what happens if you use more than 2 layers?
Oh, I didn't try. I would expect that at some layer between the second and the last layer, it would compute this reversed pattern. And all the others would probably basically look like noise, because it would be not using them, right? It could just use the skip connection. But that's a hypothesis. I didn't try. So good question. My expectation is that anywhere that it doesn't need an attention head, it will kind of just fill it with noise. But maybe it will do something else. Okay, so here's a different example. We're going to compute histograms. So we're going to count at every position in the input sequence how many other tokens have the same value. So for example, on hello, all tokens but the L's appear only once. And we are assuming a beginning of sequence token, which we ignore and just give it, the value 0 or 1 or some default value. We are assuming a beginning of sequence token that isn't important for the output in this task. Okay, so how would we approach histograms? Here's a reminder. For length, what we did was we sent a 1 from a single position and did the selection pattern that chose all positions. And in this way, we got the inverted value of what we wanted, which was, how many values have we looked at? And that's how we computed length. And so can we use a similar trick for histograms? And there is actually a challenge. Does anyone have a guess what the challenge is if we wanted to apply the same trick to compute histograms? I'll give you 5 seconds so as not to hold everyone up too much. Okay, so the challenge is that for length, we sent the 1 from the first position. But now, if we try to do the same with histograms, focusing every token on the tokens that are the same as itself, we wouldn't know where to send the 1 from. So for histograms, we're going to have to do a different trick. And what we're actually going to do is we're going to take advantage of the beginning of sequence token, although we can also do it without, but that's a separate issue. So for this example, I'm going to create the selector that focuses every token on the tokens that are the same as itself, but also on the first position, on the beginning of sequence token. And in this way, when I compute the fraction, I can just send a 1 from the 0th position, which gives me 1 over the number of tokens the same as myself plus 1, because I've also counted the first position. And then I just get to compute the inverse and correct for that 1 additional token, and that's how I compute histograms. So I still manage to get my histograms. So that's how I compute histograms in RASP when I'm assuming a beginning of sequence token. And if we check this, this compiles to a single attention head. We have a single selector taking part, and it's not taking advantage of length or something else hidden. So we have 1 attention head, and it focuses each position on positions that have the same token as itself, and on the first position. So this on the left is how the selector pattern looks for the input sequence JibbyJig. And on the right, we train a transformer on the same task, and then we draw its attention pattern on this same input sequence, and we really see that it's learned the same attention pattern. That's not a transformer that we encouraged to reach this attention pattern. It was just the natural solution that it learned for this task, which I think is quite cool. So at least sometimes the RASP programs are similar to the natural solutions that are transformed. Yes.
So I see some of those squares are not blue, right? So there's the 0.4, the 0.6 are a bit off. Do you have kind of any...
Where is the 0.4? Yes.
Okay, so do you have some intuition as to how to help it calibrate, or what's needed to... Is it just going to stabilize after a few epochs, or how are you going to...
My assumption is that it would stabilize. I would hope. I don't know how to...
Yep.
I haven't researched how to help it.
Yeah, it's a soft question. Cool. Yeah.
What's that?
It was a soft question, so you've answered. Thanks.
Okay. All right. So that's but just to note, when it says 0.3, that's not that it's the first row, the second row, saying 0.3, 0.4, 0.3. That is actually success, because it has to distribute its attention evenly over the selected positions. so approximately a third to each one. But yeah, when it's 0.6, 0.4, it seems a tiny bit off. So yeah. Anyway, so let's look onto what this gives us. So what kind of insight do we get for this? Well, for example, there's the universal transformer, which sort of gives the transformer its own control mechanism where it can decide to repeat a layer a certain number of times until it decides that it's done as a function of the input. And that would give us unbounded loops in RASP, right? So right now, RASP doesn't loop except for meta loops where it just repeats a certain layer a given number of times. But this is a sort of input-dependent loop, which is interesting and would increase the power of RASP. RASP simply cannot do a computation that's more complicated than n squared because it has a finite number of operations. Any code segment has a finite number of operations. No loops. The maximum complexity of an operation is n squared. The universal transformer would be like increasing the power of RASP. So that's interesting. It sort of motivates the results of the sandwich transformer, where they observe that if we reorder and switch the attention and the feed-forward sublayers, the multi-head attention and the feed-forward, they found, for example, that if they just have a lot of feed-forward sublayers at the beginning, that's not very powerful. And that kind of makes sense because we know that if we only apply the element-wise operations to our tokens and our indices, we're never going to know more than just the current token and index, and we haven't gathered information yet. We haven't applied any selectors yet. So that's interesting. It's also interesting that only the attention, just a layer is, you know, a set of layers that are just attention is not enough. And kind of makes sense because they don't give us these element-wise operations, they just average values, and we do want to get insight from these values. And another insight, which I don't know if I have enough time for, is that transformers use at least n log n of the n squared computational cost they have. So a transformer is definitely going to take n squared time to run, where n is your input sequence length. But at least, given that in RASP we can implement sorting, which we know requires at least n log n, then at least we feel, okay, at least whatever we're doing there, expensive as it is can take advantage of at least n log n of these operations, which is nice. I don't have time to go into how we do sort, but if you follow that, the general idea is each token counts similarly to histogram. It counts how many tokens should appear before itself, that is, has a lower value than itself or has the same value as itself but already appears before. And then knowing how many tokens appear before you, you know where you should be in the sequence. And then another attention pattern takes every token to where it should be. So that's nice. I don't know if there's a program that takes advantage of all n squared of the attention head costs. And that's it. I'm sorry. I mean, I'm happy to stay if anyone has questions.
That's great. Thanks.
Sorry if I took all the time.
Yeah, no, that's good. Also right on time. So does anyone have a question? Raise your hand or ask in the chat.
If no one has questions, I have questions.
I have a long list of questions, but I'm more curious to hear what you have to say. So let's let you continue. Yes.
Oh no, these are optional questions. So
oh, I see. I see.
Yeah.
Oh yeah.
Optional talks.
Okay, so everyone's now clapping in the chat. Virtual clapping. Yeah, you can see the messages. Thanks.
Oh, that's nice.
Yeah, so I have a long list, so I'll ask until someone else interrupts or we run out of time, if that's okay.
Mm-hmm.
So here we you know, we're interested in verification, right? So you found those building blocks that you can then put together, you know, using your Python code. Do you have any ideas how you can use to specify that something is correct or that at least doesn't diverge from some, you know, wanted bounds and so on? Or have you thought at all about how to incorporate some verification?
You mean being reasonable, so to speak, of
reasonable, or avoiding really bad behaviors, or you know, anything really?
I guess if you mean reasonable with respect to whether a transformer can implement it, it's a good question. It's not one we've approached. If you mean safety, my impression, and I'm not in programming language, but my impression is because RASP is quite a small language, then hopefully applying verification methods to it should be quite straightforward, especially given that it doesn't have unbounded loops and so on.
Right. Thanks. I have another question if there's none from the audience. So you've come up with a little collection of like a library of learned transformers, right? Do you think you can use them to do some reverse engineering? So if someone has like a train network that seems to work, then you try to match different sub collections of layers with your library to try to.
Very, very cool. We haven't done it yet. It's definitely something that we are thinking about.
Great.
It would be extremely difficult.
No, I believe that.
But it would be the very cool thing to do next. Yeah.
Okay, thanks. I have another question. Sorry if that's oh.
I'm happy.
Yeah. Okay. So how do you kind of glue these things together? Is it just Python code that kind of puts things together? You know, this is like all embedded in Python, and you kind of constructing the RASP, you know, collections of layers. Yeah.
I mean, we have a full interpreter, so rest assured you would not be writing Python code, but the interpreter is implemented in Python, and the underlying created objects are in Python.
Okay. Right.
Thanks. It's not a sort of softly embedded language. It's a complete language with a grammar and interpreter.
Right.
If that's what.
Right. Okay. Last question, because I am holding the stage, and people, you know, it's the last talk of the day or whatever. Can you pre-calculate some kind of backprop through those RASP primitives so you can get more efficient? Do you know what I mean? Like caching on the backprop for the RASP primitives. Does this make sense?
We cache computed operations, if only because it would be terribly slow otherwise if a variable was being used multiple times. So we use memoization in the underlying implementation, but with respect to backprop, so RASP doesn't create an actual transformer. It's a symbolic language. So we wouldn't be, at least now, we wouldn't be backpropagating through it. When we compile the RASP code, we get an idea of how many layers and heads we would need in a transformer that implements the same task, and what kind of attention patterns that transformer should be creating. But we don't, I wouldn't be sure what we would backprop through RASP itself. It's more about understanding what the transformer is doing rather than learning in that sense.
Right. Thanks.